Okay, let us begin the class. I want to discuss about frequency response today, and then next week we will enter the border plots concept. I want to remind you again on the project. How is it going, the project? You see, you can get plus 10 points for exam 1, 2, and 3 if in the end your system works. Your system has to work in the end, and then I can give you plus 10 points for exam 1, 2, and 3. You see, for the step number 1, your step is less satisfactory than the other group, right? So it may not be get full 10 points, but you can still get additional points if your system works. So yeah, you have to revise your system. Yes, you can consider step number 1 goes to exam 1, step number 2 goes to exam 2, step number 3 goes to exam 2. Okay, and then in the end, if you are using the LQR, you can get 100 in exam number 3. Oh, you have to take it, of course. There is no guarantee your LQR working, right? A linear quadratic regulator controller. It's a type of controller. If we have time, I don't know. Yeah, for one group. Yeah, for one group. Yeah, most likely LQR you have to learn it on your own, which is why I will give you 100. Yeah, the time in here is not permitted. Too constraining. But PID is still okay. PID is still okay. One input, one output. Your system is single input, single output, so you can use PID. Okay. I want to review first about control system design that we learned so far. An example, if you have a drone like this, you want to make it hover, moving towards the trajectory that you predefined. So when you create the block diagram, you will have the plant, sensor, and also your controller. Okay. Your job is to design the controller. Okay. Anyone remember what's the goal in designing the controller? What's the goal? Okay, what else? Okay, what else? Yeah, that one is included. Fast response is yeah. You haven't mentioned one important thing. Yeah, stability, correct. Okay. So you want to stabilize it. Okay, this one is related to the final value, rejecting the disturbance. Okay, and then we also have answered the question of this: how to achieve this? Design what? Yeah, how to design the good controller? Identify the plan. Okay, let's say we have identified the plan. Then how do we achieve this? Yeah, how to design the controller? Like this. Okay. So you know the characteristic of your system, so you can define your dominant poles. Okay. You know why it is called characteristic equation? Because it defines the characteristic of the system. Okay. What else? After you define the dominant poles, and what you can do? You forget this? Yeah, of course. We design the controller based on this. Yeah, and then yeah, you can do this to check whether your output can track the reference. Okay. You also have to check the steady state behavior of your system. For figure A here, where is the dominant pole? This one? Yeah, the one that is closer to the imaginary axis. Okay. What about B here? Okay, the real one is that one's the dominant pole. So it is the opposite of our idea. Yeah. What about this? Huh? You need to know measurement. Closest to zero. It's unstable. Yeah, we are not interested with dominant poles in this situation, okay? Because it is unstable. Okay. How do we select the controller so that closed loop poles are at the desired poles? Yeah, so we know, let's say this is our desired poles. How do we select the controller so that the closed loop poles are at our desired poles? How to do that? Okay, compensator like this one. Okay, this is root locus. Boundary condition is in MBM, not in this class. Yeah, test point is in the locus. Actually, we learned about two methods so far. Okay, two methods: root locus and then the parameter matching methods. Parameter matching method. I don't know whether you remember or not. You assume a form of the controller, let's say P, PID, or PI, and then you expand the closed loop transfer function. And then you also expand the characteristic equation based on the desired poles. Okay, and then you match the coefficient between the two equations. After that, you can determine the parameter P, PI, PID, or lead lag, and etc. Okay. So these are the things that we learned so far. Yeah. You have been equipped. Equipped is maybe not the correct word. Yeah. But you have learned so far about designing a controller based on root locus and also using parameter matching method. Okay. Now we enter the new topic, which is frequency response. So frequency response is another method in designing the controller. Okay, and we can also combine the frequency response method with root locus to design the controller. There are three methods that we can use: Bode, Nyquist, Nichols. So these are the three person that develop the techniques. Yeah, they are not in this world anymore. Yeah, and so the name are there. So if you can find a new method that is so fundamental, maybe you can your name can be there, but after you die, of course. Okay. Yeah. One interesting statement here is that when you are using the frequency response method, you can design the controller by using measurement data. Yeah. which you will use in to get the transfer function from your project. Okay. Now let us define what is frequency response. Literally, it is the steady state response, okay, to sinusoidal input. We have transient response of a system, we have steady state response of a system. Only these two things, yeah, transient and steady state. Why we don't interested with transient response for the frequency response? Anyone can answer?
Always subjected to engine.
No, not that one. Not that one. No, not that one. What is the meaning of transient?
Still changing.
Still changing. Okay. Will it be forever? Okay. So transient is just for a while, temporary. Okay. So after a while, it will die out. Yeah. And then you will be left with only the steady state response. Which is why when we are discussing frequency response, it is the steady state response that we are interested in. Okay. So let us see. A very simple system. Is it stable? Root locus. Remember what's the root locus of this? How many poles? One. Okay. One pole. And then how does it look like then? Just going to the asymptote to the left, yeah. Okay. Yeah, good.
No
good.
zero.
Huh?
No zero.
Yeah, no zero.
Yeah.
So let's say we are giving it a sinusoid input like this. What will become of the output? Anyone know? How? Yeah, how do we get it? You multiply. We want to get the CT. Okay, Laplace. Before you do the Laplace, partial fraction. Correct. Okay. Yes. If you're like this, you don't have to write down the formula there.
Iya dia
Okay. So you see, we just multiply the input and then the transfer function. Okay, like this one. And then this is the partial fraction expansion. We have A and A bar. Why is that so? Anyone know? What is this A and A bar? Hat is this one. Bar is that. What is A and A bar? Can anyone guess? Okay, what is the roots of S square plus omega square? What's the roots of that?
S minus omega S omega S negatif omega S minus omega. Oh.
Okay, you write down S square plus omega square equal to 0. So S square is minus omega square. So what is S? Is the square root of minus omega square. So what is the square root of this?
Omega J.
So plus minus J omega.
J and I is same, sir.
Huh?
J and I is same.
Oh, you said I just now?
Yes.
Oh, okay, yeah.
That's the same thing, right, sir?
That's the same thing. I and J. Same.
Why sometimes we use J and why sometimes we use I? When you already use I, you use J. Biasanya kan kayak gitu, tapi kan berapa subjek yang ada.
Yeah, MATLAB uses I. Okay. MATLAB uses I. The book uses J. The book uses J. So I match it with the book because later on you will use the book. to read more.
So this is not vector.
It is a vector. This is a vector, right? This one vector?
The ing. The right.
No, not a vector. Okay, it's just an index showing it is an imaginary number. So the roots of that is imaginary number. Okay, which is why it appears here, yeah, plus j omega minus j omega. So what about a and a bar? Yes, it is a constant. Why do we call it a and a bar, not a1, a2? Yeah. So what is that?
Because if you do the partial fraction, it will have
Yeah. What pair? Yeah. What do we call that?
complex.
Yes, complex conjugate. Okay. So that's the complex conjugate. Yeah, based on this, so we know that this will be the full solution to the CT. Okay, you recognize this? Yeah, this is the part that will go to zero. This part will go to zero. So the steady state will be only this two. Yeah, this one will remain. This one, as time goes to infinity, it will die out. Agree with me? Yeah. And so this is how we get A and A bar. That's the derivation. A is the parameters, the coefficient for this. What BK? Capital A is the amplitude of the sinusoid function. Yeah. And so you see this g of j omega. Yeah. What is g of j omega? G of j omega. What is this? No. Yeah, we put g omega into g. Yeah, okay. So if g of s is 1 over s plus 1, then what is this?
J omega plus 1.
Okay, yeah. So you just replace s with j omega. And so because of that, the g of j omega, is it complex or is it real? This one. It's complex, right? So when it is complex, we can express it as this one. Okay, we have a magnitude, and then this is the unit factor. Unit factor. Sorry? Magnitude is the absolute value. Okay. And the unit factor here, it has the angle phi, yeah? Not pi, phi. PHI. Pi and pi. This is PHI, okay? And how do you get the phi just now? You get the angle of the transfer function, tan inverse of the imaginary part divided by the real part of it. Yeah. So how do we get the magnitude of G omega then? Yeah, you just put the J omega here and then you take the magnitude. Yeah, the magnitude, how do you get the magnitude? Yeah. The magnitude of the top one is just 1, yeah? And this one, square root of 1 plus omega square. Okay. That is for 1 over s plus 1. If gs is something else, then of course you have to replace. Yeah. So don't don't use this for all of the g. Yeah? This is just for 1 over s plus 1. What? This one? It depends on the omega, right? Yeah, the thing is that when we are plotting this, you have to insert the omega. Yeah, omega is from 0, let's say, up to 100. So you put when omega is 0, what happened with this? Okay, and then omega is 0.01, you plot again the magnitude. So omega is just the variable t lah in time domain, the t. Yeah, we are not supposed to solve it until we get the closed form solution or taking out the omega. No, you replace the omega with the range that you want. Yeah, omega in that case is the frequency of the sinusoid. Yeah. What?
It's JW with J omega squared, right?
Oh, it's minus. Yeah, it's minus. No. It's plus. We only take the imaginary part. Okay, so when you are doing this, then this is the imaginary square plus real square. So you take only the imaginary part. The j is not included. Okay. Let's say I have f is equal to 3 plus 5j.
Imaginary part is 5.
What is this? This is 3 square plus 5 square.
Oh.
Yes, square root of 9 plus 25. No, it is 1, right? We have only the real part of it. No imaginary part.
Yeah.
Okay? Yeah. This one? Yeah. Why is that so? Okay. Yeah, there is a question on the parameter A here. So let's take a look. Yeah. We are using this equation. Okay. This equation. Yeah, in fact, this is our GS. Okay. This is the GS. What happened if I put S equal to minus J omega here? We are not using this. Yeah, this is not exist anymore. Okay. If I put S equal to minus J omega here, then what happened? The difference will be 0. Yeah. So this portion will be very, very large. This one will be small compared to this. So I can remove this. Okay, so that means A is equal to this portion multiplied by that.
A is equal to that portion multiplied by the S plus.
Yes, which you come here. Okay.
Oh.
Okay. Yes, dominant one. Yeah, conversely, when we put S equal to J omega here, okay, then this portion here will become small, 0, yeah. So this part will be very, very large compared to this. Then this part is gone, and A bar is this whole thing multiplied by that.
So we determine the A bar by that.
Yes.
S.
Yeah. If we are using the standard method of multiplying left and right by S square plus omega square times S plus 1, we will not obtain the GS and this A over S square plus omega square in its original form. You won't get it in its original form. It is still correct, but the format is different. But we want to use this form. Yeah. The traditional method will work for finding something else solution lah. But for this solution, we will not get our what we want. We want to get this. Okay? So the term A and A bar will be in the term of G of J omega. Stephen, you just get the good grades on exam 2, so don't. Yeah. You have to keep awake. Which one? This one? No, you don't have to think about how you derive it. Okay. You think about how we use the G of J omega. Okay. So let us conclude here. So this will be the steady state solution, and then this is the value of A and A bar. Okay. And then if we put A and A bar into this solution, so we put A here and then A bar there, then we will get this. Okay, agree?
Yeah, agree.
So E minus J omega T and E J omega T are still there. Okay, no changes on it. And then what happened is that if we multiply, we get this. Okay. Now we multiply this will be that one. If we multiply this one, we will get this. So we just flip the order. Okay. After that, this portion will be the sine omega t plus phi. And then this part over here, it will be the amplitude of our output. Okay. Sinusoid function. Yeah, this is a sinusoid function, but it has a phase shift, which is phi, and then the amplitude is c. So amplitude will be c. So what is c related to the A? Yeah, that's correct. So let's say you perform an experiment. You know what's the amplitude of the input, you know what's the output of your output. At that particular frequency, you can obtain the absolute value of GJ omega. What if you get for a whole range of frequency? Then you can reverse back to get the transfer function. Okay. So you see, this is the steady state value, yeah. And then this is just to summarize, yeah. To summarize, Stephen, what's your question?
That A equal to, so for the question, A equal to C, E omega C.
A is yeah.
So we insert A in there, right? So
No, A is something that we know.
I think what we meant is if A times EJ, A times the magnitude of J, T of J omega equals to C, why does it become EJ omega magnitude equals to A over C? It's really
Okay, this one, yeah, I want to highlight this because you can obtain the magnitude of your transfer function from the experiment. Yes. Okay. So you can estimate the transfer function of your system. Yeah. So you can do the same experiment on your model, the bicopter. Yeah. Give it a sinusoid input, it will doing the chungkelik chungkedang thing. Yeah. And then you can record what is the amplitude. Yeah. Yeah, sinusoid input only. Oh, of course not. Yeah. Frequency response. Yeah, step doesn't have frequency. Chris first.
No, A is the output,
Yeah.
C is the output.
Yeah.
Why do you choose this one?
Why square? No. This one is equal to this, right?
Yeah, I think one of the questions is I don't know, A.
Sorry. I think I reverse it. Sorry, it's I reverse. Yeah. Sorry, it is C over A. Yeah, good point, Stephen. Good point. Yeah, you can get bonus points.
Tadi saya juga mau. Udah lah, stop nonton Marco lah.
Okay. So it will be you write something? Yeah. So it is C over A. Yeah. Okay. Thank you, Stephen. Yeah. So this will be the amplitude ratio. Okay. And then this will be the phase shift. Yeah. An example, if we have our transfer function just now, and then we give sinusoid input of sine 3t. Yeah. The output will be like this, so you can see that the amplitude is different. Yeah. And then you recognize that there is a phase shift. Okay. So you see, this is the C, this is the A. Yeah, and then so that will be the magnitude. Say it again.
Yang transferannya selesai itu, aku pilih graf.
Oh, if it is unstable, you cannot plot. No, you cannot do the experiment.
Like, what to see how the blood looks like.
Oh,
It's
you just go like this.
like this.
Yeah, if your system is unstable, then the plus b portion, it will be e to the power of t, not minus t. Yeah, so it will be go like this, but then it will oscillate like that. Yeah, you see that? Yeah. Okay.
The C is the amplitude after the phase.
Not after the phase shift, but after it is reaching the steady state. Yeah. You can see in here the height is different, right? Yeah. So we don't measure it here. After steady state, you measure the C.
Do we need to know when it
System will eventually reach steady state. Yeah. Let's say you wait 1 minute, steady state. Yeah. For dynamical system like this, 1 minute you reach the steady state already. Fast. Yeah. The quadcopter, the bicopter. However, for the CPU cooler that you did several weeks ago, that one will take some time to steady state. Yeah. The response is slow on that. Yeah.
So like what does we want like small ratio?
No. In this case, we only identify the behavior of the system. Okay. At this frequency, this is the behavior of the system. Okay. When you change the frequency, the amplitude ratio will be different. Yeah. It will be different. and that kind of behavior is something that you want to know, so that you can identify the transfer function of the system. Yeah, it will react faster if let's say your system have high bandwidth. Okay.
Like outside.
Which original? This one? Oh, 3 radian per second.
So
Yeah.
between is
The C, yeah, in this case it will decrease. Yeah.
so higher the ratio,
Higher the frequency, yeah, most likely you will get lower C
for this transfer.
for this kind of transfer function.
Oh,
Ansel, go here. Yeah. Okay, you face there, and then you sit down again. Ansel, come here. Sit down. Come here, sit down. You see, the amplitude becomes smaller, right?
Oh.
Because his reaction is not that fast. Yeah. Yeah, correct. Before he reach here, I tell him to go back again, right? And then there is a delay, right? The delay is the phase shift. Yeah.
selalu
Yeah. Okay. For a physical system, it is usually lagging. Yeah. So it's minus for a physical system. If the phase shift is leading, what do you think will happen? Before I tell answer come here, you're here, come here. Cannot happen, right? So yeah, physical system will have negative phase shift. Now I will give an example. Yeah, this plot only for one particular frequency. What if, let's say I plot G of J omega and also the phi for frequency ranging from here 0.01 up to 100. Then I plot it. No, only one plot.
Only one plot.
Nah, that's right. Many point lah. Okay. So this is the result. Okay. So Bode plot, we convert the magnitude into dB, decibels. Yeah. We want to convert into a logarithmic plot. So in dB, it will be 20 log 10, yeah, of the G of J omega. Okay. 20 times log of G of J omega. Then you will get the magnitude here in decibels. No, the magnitude, not the magnitude. Yeah, the magnitude of the transfer function. No, in this situation, C is not so important. Okay. The most important thing is how the shape of this body diagram. Okay. You can see this is 1 radian per second, yeah, 1, yeah. After beyond 1 radian per second, you can see that the magnitude becomes small, yeah. So that means the bandwidth is around 1 radian per second. If I give an input to the system greater than 1 radian per second, the system will react slower. Magnitude will become small. Yeah, you can see that the phase shift also changes. Yeah, in here the phase shift is not so big. Yeah, beyond 1 radian per second, you can see becomes minus. 90 degree. Okay, so this is the behavior of the system when we change the frequency. Yeah, and then for S plus 1. Oh, second order is more interesting. It will have a peak. If it has a natural frequency damping ratio less than 1, it will have a peak. A peak in the area, peak and then go down. Peak, not the Pantai Indah Kapuk ya. Yeah. How do you get this plot? Just go to MATLAB, write down the body of the system.
Diagram.
Yeah, one is the magnitude, one is the phase.
Let's go.
What one? Which one? This shape? Yeah, up to you how to interpret it. That's the shape. Okay. There is also a possibility of phase shift 180 degree. Yeah, it is for some system. What happened when it is 180 degree? What do you think?
It next by half.
It goes the opposite. I tell Ansel to go here, Ansel go there. They cannot keep up anymore. If let's say you have your capstone, you have 5 supervisors. 5 supervisors telling you, yeah. In one day, each supervisor give you a job, a task. Until one time you don't know how to react, right? You will submit to me the job that given by Pak Farid, let's say, yeah, because of the confusion that you have. Okay, and any question related to this? Okay, so sorry. Yeah, you have to change the pole. Yeah, and then the one that you will plot here is the open loop pole. Yeah, open loop transfer function.
H.
Not necessarily GH. Yeah, it is the compensator multiplied by the G. Okay, so we are going to assume that the H is 1 because later on in the experiment it is 1. Yeah, there is no feedback on that. So when you are introducing the compensator, you can change the the pole location. You can change the value of this bandwidth. Okay, you can shift this more to the right side. So if you are designing a system, your system should work in the range of this frequency. Okay, for a very good response. Okay, I tell you to go 5, you will do 4, let's say, not so bad. Okay, if you are working in this region, then that's not good. Yeah. Not slow frequency. It's a frequency within the bandwidth. Within the bandwidth. Okay. This is the thing that I told you last time. Group number 1, next week you will explain about sketching the border diagram. Who's group 1? You. Alfie, one more.
Yeah, I'll do one more.
Where's Alfie? 3%.
Oh, kami dua. Oh, the group two.
Anthony, no, Anthony will come next week, right?
Yes. November.
Who's group 2? You're group 2. Okay, group 2, this one. Group 3 is group 3, yeah. Gain margin, phase margin. So the gain margin, phase margin, we can assess the stability of the system.
Maksudnya kita ya bisa ini. Itu kita ngajar.
Yeah. You are teaching the class. Okay.
Dari
There is no homework.
Homework. This is
No homework.
At the end, sir.
Until the end, there's no homework.
Yes, this is homework. It's waiting for the presentation. The rubric.
The grading. The rubric, you need the rubric.
Nilainya kemana?
The point will be going to your homework and then the bonus point.
Tapi kan di sini kan belum sampai.
Yeah, I will put all of the homework from here, from the discussion, from your activity in class. So let's say when group number 1 is presenting or teaching in the class, all of the groups have to be active if you want to get bonus point and good grades on your homework. Okay, you all have to take part. Okay, so prepare yourself, yeah, before coming to the class. And then the source for body plot, nucleus plot is chapter 7 of this book. Do you have this book? No, it's not in the D12. Also, other module will be in the canvas. It's the entire class. Huh? Yeah, we cut it, of course. It is necessary for you to have a discussion. Yes. Yep. So you can discuss problem and examples. Also, yeah. 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 If there is too much interruption from myself, then the bonus point will be small. I don't get bonus point. I don't need. I don't need bonus.
Kalau kita salah ngajarin gimana?
Yeah, I will jump in, of course. If you do it wrongly, I will jump in. Yeah, I won't let you to learn wrong thing, of course. Yeah, and it will reduce your point. Okay. About the rubric will be about the correctness of the material. Yeah, the first one is the correctness of the material. Is your material correct or not? And then the second one is the activity of the class itself. If the class is very active, you get high grade. Okay, so you have to invite people to join in. Okay. So that ends the class here. Any more questions? We can go to MATLAB. For example, yeah. I will give you an example for second order system. Yes. What kind of second order system that you think of?
S squared plus 0.6 S plus 436.
Damping ratio is so small, eh? Okay, then you write down border of G. This
Yeah, I mean,
That is a peak.
what's the input? The input and the
What
output.
Hmm?
What is the input to the system?
It's a sinusoid.
So like one side, one thing.
Now the input is not important. Yeah, because we are just getting the g of j omega. You see, j omega is just the ratio. Okay, so the input itself is not important. The input magnitude, the input amplitude is not important because the top part, the magnitude here is giving you the ratio between output and the input.
Ratio.
Yeah,
Yeah.
this part is the ratio. Yeah, you see the phase angle shift here become minus 180. Yeah, so it becomes opposite direction after it passes through the natural frequency. Yeah, you become someone else.
Plus like ideally you the ratio same value
For that particular situation, yeah.
But this
If you are let's say a good example is actually a hard disk drive. Yeah, hard disk drive. You are not living in the era of hard disk drive, right? But it is still used. It is still used today. And also another good example is the CNC machine and also 3D printer. Okay, let's say this is the 3D printer head, yeah, and then the filament is going here. Okay, do you want to print your project one day, 1 year, or you want it to print it in 1 hour? So you have to move fast, right? If you want it to move very fast, then you have to push your system to have this bandwidth very, very large. Okay, you don't want it to have go to different direction than your input, right? So which is why that graph is there. That is for one kind of purpose. Okay, one kind of purpose. Another kind of purpose is that we identify the transfer function of a system. Let's say you do an experiment, that is your transfer function. Then you do something, you add a controller to it, and it becomes a new system. But then your new system have desired poles, let's say, and then you design the system based on root locus. That's another way of using the border plot. So it is not always using the system in this region. It's not always like that. You know the car suspension? The car suspension is working in this region. Yeah, not in this region. Yeah, you realize that? Yeah, because when a car moving very fast, the input frequency to the car suspension has a very high frequency compared to the suspension natural frequency. Suspension natural frequency ranging from 1 Hz to 2 Hz for passenger car. Okay, what else? The engine mounting for a car. In which region do you think it was? Is it before natural frequency or after natural frequency? Why? What do you think? Your idea? What's your idea? Engine mounting should act here or on the right side? Okay, Chris, what do you think? For engine mounting, is it here or there?
Whereas I still don't see like why we have where the purpose of
The purpose of
because my logic is like what I think is like we want to have a steady state. So we want some value. And the way how I see it is like first part over there where it's stable is that
no, we are not plotting stable or not stable in this case, because this is frequency versus magnitude.
they're not related.
What?
They're not related. Are they not related?
Just now you said become stable. You are referring to time domain response just now.
Oh,
So okay, then what else?
how is
Magnitude related to the steady state. Just now we discussed about this, yeah. The steady state value of our system is that is the A multiplied by and then multiplied by this. Okay. So we will know our steady state value or our steady state response by having this input multiplied by the ratio and then multiplied by the sinusoid function itself. So this is the relationship. And then your question?
so like so that's the C.
Yeah, this is the C. Correct.
Like what does it tell us? What is it?
It tells you the response of a system after you give it a sinusoid input.
Okay. Like
Okay, mechanical system. What kind of input that you can think of that can be given to a mechanical system? What kind of input? Step input. Step input. What's the example of a system having step input? Stepper motor is rotating. Lights, yeah. Yeah, lights is okay. Yeah. What else? What kind of input? What else? What machine? What machine? Lighting machine is a step input. Yes, yes. What kind of input? Other input that you can think of? Cars? Yeah, what type of input? We have. We have.
I don't know. I think volts.
Okay, we have periodic input. Okay, periodic input. It can be written as Fourier series, right? So in Fourier series, you have sine and cosine, which is the domain of our frequency response. What about the car's vibration? What is the input from the car's vibration?
So if they share equal vibration,
Do you agree it is sinusoid? Yeah. So you have to know what kind of response that your system can have if you have multiples of input, different type of input. You need to know what will be their response. Do you agree with me? Okay. So which is why we are learning on how to get the steady state response when your system is subjected to sinusoid input.
So like the end result. What do you want to find?
We want to draw the border diagram. Okay.
So that it's stable.
No.
So
Stability later.
like this, like, you have step input, and if the function is like this, now you will have the input, and the resulting input is like still like frequency, but it has different properties, like the rhythm is different, and there is phase lag.
And now we're trying to plot the properties.
Yeah, it is only for one frequency, right? When we change the frequency, the system will have different behavior. That's why we put the
So what is it?
see the amplitude after
C is the
we
amplitude.
apply.
This is the C just now, Chris. Okay, the C is here. Okay, that's the amplitude of your output. Yeah, when it is reaching the steady state.
See and different is like
Trying to plot the frequency.
okay.
Because like the most important is
The what?
C at the beginning.
Yeah, the C. Which C?
The first shift, the first. Not in the same graph.
Which one?
First.
Oh, this one. This is not C. It's not C. I'm saying that, in the beginning, it still have the transient effect in here.
That's in the end, bro.
Do you follow the discussion just now? That we have this. You see, we have this. Okay, the CT is having this. Okay, and this one will die out. Okay, that's the part that is dying out. Okay. So this part just now dying out. This much is dying out. Okay. Is this clear now?
But I still don't know what C is.
What the C is? This one?
Yes.
You mean what do you mean? Do you not understand what the C is?
Like after I get to see like what is it telling me?
Oh, the C is giving you the amplitude of the output at steady state.
Will it tell me like I want to see A.
Oh, stability you will see from the border plot. Stability you can see from the border plot, but not because of it is flat or slope. Okay. Stability later we will learn from the border plot, not from this plot, not from here.
So this is just like standing still for this.
Yeah, we are building the knowledge that this will be the response of the system for one particular input frequency. Okay, and then I'm telling you that if we change the frequency input, you will get a different output. You will get different C again. Different C. Same A, the A is the same, but then the C will be different. No. If we change the frequency, input frequency we change.
Maybe we have the magnitude first.
Yeah, you see, if we change the frequency of input from C will be different. Yeah, and then if we take the ratio between the C and A, We get this
Oh, okay.
for different frequency.
Okay, that makes sense.
Okay. Now from here we can study the stability of system.